Well. Now we're on to the operations of complex numbers variables, known as the imaginary I. Now, I strongly advise you guys, before you go ahead and proceed, remember your powers of I, the imaginary term. I equal to the square root of -1, or I squared equal to -1, I cubed minus I to the fourth, a positive I. Now, this complex variable is z, and we are given it. It's equivalent to the x component, which is the real part, plus I times y, the imaginary part, the y component. This will be our complex variable we represent on the complex plane. In a future video, I'll try to show complex variables graphically, if I can. So here, in this very first example, we have z equal to 5 plus 3i. Now, in these little component parts, we want to find the REZ. REZ is just a fancy notation of the complex variable known as the real part of z. Real part of z being 5. Part B is the imaginary z. Now, the imaginary z is written... This is a notation of the imaginary part of z. The imaginary part being a 3. The real z plus the imaginary z. You just add up 5 plus 3 and you get 8. Now, square root of 7 times imaginary z is equal to 3 root 7. Z can also be written as the components of z is equivalent to real z plus I times imaginary z, equal to x plus iy. Let's set up all these complex variable cases, notation of the complex number, in a standardized form. A is 7i. B is 4. C, the real part, is 1 over 9. The imaginary part is 6. Now, standard form just means z equals x plus iy form. Or a fancier way of saying that is z equal to real z plus I times the imaginary z. Now, A is written in standard form as z equals 0 plus 7i, because the real part of that the real part is 0. B, it's z equal to 4 plus 0i. There is no imaginary part, it's just a 0, while the real part still remains intact as 4. Now, for C, you have z equal to 1 over 9 as the real part, plus 6 times I as the imaginary part. Here's some radicals with a negative in front. As mentioned earlier, square root of -1 is equal to I. Here are just some of the examples of radicals with a negative in front of them. Be sure to verify these, since they are square roots. Now, for complex variables, there are orders of operations involved with them as well. Addition rule. 5 plus 3i plus 2 plus 2i. Only add up the real component parts, and you add up only the imaginary component parts to give you the answer of 7 plus 5i. The real part plus the real part is 5 plus 2. Imaginary part of that addition is 3 plus 2 is equal to 5i. Now, subtraction, you just do the same. Just remember to FOIL out the negative if you don't like negative being there out in front of the parentheses. 5 plus 3i plus or minus 2 minus 2i. This will be 5 minus 2 is 3. And 3 minus 2 is I. 3 plus I. That is what you get after you do the subtraction rule of the subtraction operation of the complex number variable. The difference of the two. Multiplication. Here I just have I, parentheses, 1 plus I. Just fill them in. I times 1 plus I times I, then I end up with I plus I squared. It's equal to I minus 1. The division. Now, division of a complex number. Most important goal. Rationalize the denominator. As we have rationalized radicals from 1 over square root of 2 in the past, we do the same exact thing for complex numbers, variables. You see, the rationalization method is we multiply the product of I over I, then you end up with IA cubed over I squared, which is just I squared is -1, so you end up with a negative term in the very end of the problem. So that is -a cubed times I. Next property is, let's suppose we know what z equals. Now, we need to find this fancy little notation symbol known as z bar. To find z bar, we know what z is given to and represented as already. So here, let's go back to z. We need to find z bar, so we apply the bar on both sides. Isn't it ironic, after you apply the bar on 5 plus 3i, the result is that? When I say that, I'm referring to z bar as the conjugate of z. 5 minus 3i is a conjugate of z in the complex variable notation. So z is the conjugate of the complex variable z. Very last example. Let's factor d squared plus 64. Now, when we used to do factoring, we weren't able to factor out d squared plus 64. Let's try setting up an equation for that. Just set it equal to 0. You know, we're trying to find the zeros of d squared plus 64, so that's one of the ways I see of doing it. Other involves quadratic formula, but I prefer just setting up an equation. D squared plus 64 is equal to 0. So now d squared is equal to negative 64. Take the square root of that negative 64, you get two roots, which are plus or minus 8i. To verify the factors, you just FOIL them back in and you get the original result. Now, d is equal to plus or minus 8i. So the factor of d squared plus 64 can be written as d plus 8i, parentheses, d minus 8i. Hope that helps. So, this concludes a little discussion on complex numbers and variables. Now, complex numbers and variables are very different from irrational, rational numbers, integers, whole numbers, natural numbers, all real numbers, negative numbers, vice versa. To summarize, to conclude with this little discussion of the imaginary I, master the power rules of I before you proceed. You must keep practicing the power rules before you learn this topic. Very useful. Understand relationships of z, x, y, real z, imaginary z, z bar being known as a conjugate, and how to obtain that conjugate. The real parts and imaginary parts have to be represented in their standardized forms, being z equals x plus iy. Even if the real part is 0, you still have to write it in complex notation, which is z equals 0 plus iy. The same laws apply with imaginary. Thank you, everybody, for watching this video. Comment, ask questions if you're unsure of something. Hope you learned something from it. Take care.